this video, we're going to look at the multiplication rule for disjoint events. Independent events. For two events A and B, the fact that A occurs does not affect the probability of event B occurring. These are two events that are independent. So one occurs, doesn't change the probability of the other occurring. Suppose you roll a dice 2 times in a row. The first time you get a 3. On the next roll, what's the probability that you get a 4? So we already know that the first roll we ended up getting a 3. Now we roll the dice again. Does that change what the probability of the next roll outcome is? So the probability of a 4 is still going to be 1 over 6. The fact that we got a 3 before doesn't change that probability because these two events are independent. You are playing a card game with 3 of your friends. You draw one card, look at it, and put it back in the deck. Then your friend picks up a card from the deck. Are these draws independent? Because you are replacing your card after you've drawn it, the original deck is still intact when your friend picks a card. So the probability of the outcome of your friend's pick doesn't change because you're starting with that original sample space unchanged. So these are independent. Let's look at an example before we define the multiplication rule. A card is drawn from a deck and replaced, and then a second card is drawn. Find the probability of getting a queen, then a diamond. So the multiplication rule, one thing you want to remember is that we're actually looking at more than one trial. So 2 or more trials. So this is in comparison to the addition rule that we learned previously, where we were trying to find the probability of just a single event or a single trial, but the probability that that one trial resulted in event A or event B. So for the multiplication rule, we're using this for really just a sequence of events. So when 2 events are independent, meaning the probability of one doesn't change the probability of the other occurring, the probability of both occurring, and I'm going to add here in a sequence, is given by this probability formula. The probability of A and B equals the probability of A times the probability of B. Now, we've seen this expression, the probability of A and B. In our previous videos, we were talking about that being the probability that they both occurred at the same time. Well, using the context of the problem that you'll be working on, this is actually representing the probability of A and then B. We just don't always speak like that. So that's why the formula is not written that way. But it is important to know that this particular rule is used when you're looking at finding, or you're trying to find the probability of a sequence of events. So going back to that example we just went through, a coin is flipped and a die is rolled. Find the probability. Oh, actually, I didn't read this one, but that's okay. A coin is flipped and a die is rolled. Find the probability of getting a head on the die and a head on the coin and a 4 on the die. So we are looking for the probability of getting heads and then 4. And I like to write out the and then. It helps me distinguish between that word and in the multiplication rule versus the and in the addition rule. Now, thinking about my 2 events, they are independent of one another. The coin toss doesn't change the probability of the outcome of rolling a die. So this is the probability of heads times the probability of rolling a 4. The probability of flipping a coin and it landing on heads is 1/2. The probability of rolling a die and it landing on 4 is 1/6. And when we're multiplying fractions, you just multiply straight across the numerators and multiply straight across the denominators. So this is 1/12. A card is drawn from a deck and replaced. Then a second card is drawn. Find the probability of getting a queen, then a diamond. Because we are replacing our first card, that makes these events independent. What do you think would happen if we didn't put the card back? And that's a question we're going to answer in maybe our next video. So the probability of getting a queen and then a diamond is equal to the probability of getting a queen times the probability of getting a diamond. Now we haven't worked with the deck of cards in a little bit, so just to recap, there are 4 queens, 1 for each suit in a deck, and our standard deck is 52 cards. And anytime we're dealing with an example that is drawing a card, we're going to assume that it's a standard deck of cards, so no jokers, just our 4 suits, 52 cards. The probability of a diamond is 1 entire suit. There are 13 cards in each diamond out of 52 cards. Multiplying across, we get 52 divided by 2,704. And a lot of times examples dealing with the deck of cards, we can simplify those fractions, not necessarily always, but I would encourage you to try just to practice simplifying using whatever technology you want to use. When we simplify this fraction, we get 1/52. A jar contains 3 red marbles, 2 blue marbles, and 5 white marbles. Right away, I'm thinking I'm probably going to need a total for probabilities, so let's add these up. There's a total of 10. A marble is selected and its color noted. Then it is replaced. A second marble is selected and the color is noted, and so on. Find the probability of the following events. Because we are replacing those marbles, these trials do become independent of one another. So the probability of selecting 2 blue marbles, so this is the probability of blue, then blue. This is the probability of blue times the probability of blue. So the probability that the first marble is blue, there are 2 blue marbles out of 10. The probability that the second marble is blue, since we've already replaced the first marble, the probability isn't going to change because we have the same jar of marbles that we started with. So that's still 2 out of 10. Multiplying across, we get 4/100, which would simplify to 1/25. Find the probability of selecting 1 blue marble and then 1 white marble. So this is the probability of blue, then white, which is the probability of blue times the probability of white. The probability that we select a blue marble is 2 out of 10. After we've replaced our first marble, the probability that we select a white marble is 5 out of 10. Multiplying across, we get 10/100 or 1/10. Find the probability of selecting a red, then a blue marble. That would be the probability of a red marble times the probability of a blue marble. Again, that replacement is what's making these events independent. The probability of a red marble would be 3 out of 10. Probability of a blue marble is 2 out of 10, which gives us 6 over 100 or 3 over 50. Find the probability of selecting a red, then a blue, then a white marble. Well, this is just an extension of that multiplication rule. It'd be the probability of red times the probability of blue times the probability of white. There are 3 red marbles, so the probability of red is 3 over 10. There are 2 blue marbles, so the probability of blue is 2 out of 10. And there are 5 white marbles, so the probability of white would be 5 out of 10. Multiplying across, we get 30 divided by 1,000, or 3 over 100. And what we've just illustrated is here, this extension, so the probability of A and B and C, so on and so forth. As long as those events are independent, it's just the product of the probabilities of those individual events. The probability that a randomly selected 24-year-old male will survive the year is 0.9986. What is the probability that 3 randomly selected 24-year-old males will survive the year? So the first question is whether or not these 3 randomly selected 24-year-old males are going to be independent of one another. And we can ask ourselves, well, if one survives, does that change the probability that the next one will survive? And we should be able to identify that that answer is no. So these are independent. So the probability that all 3 survive is equal to the probability that the first survives times the probability that the second survives times the probability that the third survives. Well, the probability that the first person survives, that first randomly selected 24-year-old male, that's that 0.9986. Well, if the first survives, that doesn't change the probability of the next surviving because they're independent. So the probability that the second person survives is still 0.9986. And likewise, if the first 2 survive, that's not going to change the probability of the third surviving. So that probability that the third survives is also 0.9986. Now this product of the same number 3 times can be written 0.9986 raised to a power of 3. And this is a little bit more efficient to type into our calculator. Not that we can't multiply 0.9986 3 times, but as we increase the number of individuals, then we certainly don't want to be typing in 0.9986 so many times. So we can use the exponent function in our calculator. If you don't know how to use your calculator to evaluate exponents, please get with your instructor and make sure that you know how to use your technology. But 0.9986 raised to the power of 3. And if we round that, we're going to get 0.996. Now, in the next one, we're looking at the probability that 20 randomly selected 24-year-old males will survive the year. Now, I don't want to go through this same technique of writing out every single individual's probability. I know that these individuals are independent, or the probability they survive is not changing from one to the next. So it's going to be 0.9986 raised to the power of 20, which is 0.972. Now, looking at these two probabilities, this first one was the probability that 3 survive, 0.996. The probability was that 20 survive, 0.972. Does it make sense that the probability decreased as we included more individuals? And why? Well, if we think about it, if we start including more and more people in our sample, then the chances that one of them doesn't survive, at least one of them, goes up, which is going to make the probability that they all survive go down. Next, we're going to look at least one probabilities, and these are related to the multiplication rule. So let's start by just identifying, what does at least one mean? Well, at least one means one or more. So the opposite, or the complement, would be none. So one or more, the opposite of one or more is none. Using the complement rule that we learned in a previous video, we know that the probability of an event plus its complement equals 1. Well, here our events are at least 1 and none. These two being our complements. We know that that sum is 1. And if we were to subtract the probability of none, from both sides, we end up with this really handy formula. The probability of at least 1 equals 1 minus the probability of none. A coin is tossed 5 times. Find the probability of getting at least 1 tail. So that at least 1 is our indicator that we're going to use this formula. And I do want to point out that this formula is only true for at least 1. It doesn't work for at least 2, at least 3. There are other ways that we work on those problems. We'll see some of those in a later video, but this particular formula only works for at least 1. So the probability of at least 1 tail is equal to 1 minus the probability of no tails. Well, we can think about that event. If we get no tails, that means we get all heads, and there's 5 tosses, so all 5 are heads. So now let's just keep working on this statement right here, the probability that all 5 are heads. Well, we know that the probability that 1 is head is 1/2, and those flips are going to be independent. So all 5 would be the probability the first is head, the second is head, the third, the fourth, the fifth are all heads. So it'd be 1/2 to the 5th power. Now we want to make sure we include that 1 minus. So we have 1 minus, and then 1/2 to the 5th would be 0.03125, or 1/32, depending on how you have your display set up. And that gives us 0.969 if we end up rounding to 3 decimal places. Or exactly would be 0.96875. Now, the reason the complement rule is really handy is because we could think about this in another way. And I'm going to illustrate it, at least just a preview of it, just to really get you all to buy into the importance of this formula. So let's think about this. We want the probability of at least one tail. Well, this would be the same as the probability of getting one tail, or two tails, or three tails, or four tails, or five tails. And each one of these ors implies the addition rule. So we want to find the probability of, let me use the same color, the probability of exactly one tail in 5 flips, plus the probability of exactly 2 tails in 5 flips, so on and so forth. Well, the probability of getting exactly one tail in 5 flips, well, that could be 1 on the first, or the second, or the third, or the fourth, or the fifth. So there's all of these different possible outcomes that we're starting to consider, which is becoming very convoluted. So while we could think of at least one in terms of an addition rule, it gets very complicated very quickly. And we're only talking about 5 flips. So hopefully you're starting to see the benefit of that at least one formula. But let's look at another example, and it'll be even more clear how important this is. Compute the probability that at least one male out of 1,000, age 24, will die during the year if the probability that a randomly selected 24-year-old male survives is 0.9986. So now we're talking about 1,000 individuals. That's a lot. So when we start thinking about combinations and different ways that, you know, we can have people die in it or survive, it becomes very tedious, and we're dealing with different types of outcomes that we wouldn't be able to keep track of easily. So what we're looking for is the probability that at least one dies. Well, the at least one rule says that the probability of at least one is equal to 1 minus the probability that none. And in this case, it's that none of them die. Well, if none of them die, that means they all survive. The probability that they all survive, that's 1,000 of them. We know the probability of survival is 0.9986. So the probability they all survive is 0.9986 to the power of 1,000. So the probability that at least one dies is 0.754, which is pretty significant of a probability, and we would expect that. You start thinking about 1,000 men, there's a good chance that one of them would die, unfortunately.